The prototype creational design pattern is one you might already be familiar with. Essentially, you start with an existing object and duplicate or clone it to create a brand new distinct object that shares all of the same values of the original but is disconnected. So if you make changes to the new object, it should in no way alter the original. We know this in computers typically as cloning or deep cloning, where if it's an object with nested objects, you have to make sure you also clone the nested objects as well. We're going to start off by importing the copy module. And actually that should be up top. And then we're going to create a class, and we'll call it person. It's one of the easier ones to understand. So we'll stick with the basics. Then we'll define the init method. And we're going to stick with just a first and a last name here. And to save time, it's just F and L name. And then we'll say self.fname is equal to fname. Let's define, that should be def, not del. Let's define a string function so we can see what we have. And that'll require self. And we'll return a formatted string. And we'll make it self.lname and self.fname. And then we can define a clone method. This is probably the best way to go about it. There are methods in that copy module that allow you to do the cloning external to the object, but the idea is you provide a method like this to the interface of the class to indicate your intentions are that this should be done, not that it can be done. Now, when you call deep copy, you have to tell it what you wish to copy, and the result is a copy. It should be a one-for-one memory copy of the other object. In this case, because we are in the clone method and we're identifying it as an instance member of person, the thing we're passing to deep copy is ourselves, the self object. That handle basically refers to this current object. I'm going to clone it. So if we were to create a person, we say p1 is equal to person, and then it'll be Smith and Bill. And I pick these names because, you know, like Bill Smith, something Williams, Jones, just because they're very common American English names. If any of you happen to have this name and you're getting tired of hearing it, I do apologize. It is sometimes hard to come up with unique names that are easily pronounceable that isn't going to necessarily be someone who actually exists. Anyway, so once we have the person, I'm going to print some information. We're going to print the person, but now I also want to print the address of the person. And you may recall from earlier lectures, the ID function, when we pass it an object, should give us the unique identifier, which is a derivative of the memory address where that object's being stored. And then we can convert that to hex just because it's easier to read then. And memory is typically laid out in powers of 2, and decimal isn't necessarily good at displaying patterns in powers of 2. But if I were to do this using hexadecimal, you'll notice when I create objects that in essence it will look very similar pattern-wise with just a few of the numbers being different, indicating it's in a slightly different memory address. Okay, so we're going to create the person. Let's just make sure it's working before we move forward. Great. So we have Bill Smith, and it's at this address. If I were to create another person, again, you'll see that the address changed. So this is creating a new object every time I do that. Now what happens if I created another person and just assigned it to P1? And I print P2 and I print the address of P2. The one thing you're going to see is they both say Pete Smith, but because this is assigning a reference object to another one, I'm just copying literally the address. So P2 is pointing to the exact same data as P1, and you can see that because if you look at the address here, it ends with 32AEF0. Guess what? 32AEF0. It is the exact same object. So this is not how we clone. If we really wanted to clone an object, and just to prove it's the same one, let me just do this real quick. P2.lname is equal to Jones. And then we'll print P1, not P2. You'll see P1 now says Jones as well, even though I altered P2. So we know that this is not really cloning an object. It is creating just a pointer to the exact same one. I want to clone. So then I'll say P3 is equal to P1.clone. And at the moment I issue the clone command, it should contain all of the same data as P1. So I'll print them both side by side. And let's go ahead and, you know what, I'm going to put a separator in here of some equal signs. That way when I run it, we can see that we're in this section of code. So you can see Bill Jones twice. Here's the difference. Let's go ahead and print the addresses of both. And we should see that they are distinctly different. You can see one ends in 28, the other ends in 60. So essentially it is what would be 32, but it's not 32 bytes away because this is hexadecimal. It's 32 hex bytes away, or 32 hex bytes away. So this is in fact two distinct objects. So if I were to change, let's change the first name to Susie on P3, and then we'll print P1 and P3 again. And you'll see now they are definitely distinct objects. So this cloning mechanism is what we use to implement the prototype pattern in Python. Do you have to make your objects clonable this way? Not necessarily. You do have to use something like this copy.deepcopy command though, because without this you're not going to be able to get a one-for-one copy of every item in the object. So why do we use something like this? Well, one of the reasons is if you have an object that has 100 parameters, or 100 attributes, excuse me, and you create it, and you have to create another object that is virtually identical with maybe only 10 of them different, you might not want to have to do another object creation where you have to pass in 90 of the same parameters and just 10 of the different ones. In something like, in that scenario, we might want to just create the first object with the 100, copy or clone it, and then just change the 10 we need. So that's one instance. But the one I typically use this for is in a system where I want to make changes to an existing object, but then if I change my mind and I want to roll back, I have the original object to basically point my code back to. So let's say you have a situation where you start with your original object and then you ask the user, okay, you can make some changes. So they start making changes, but instead of clicking the OK button to submit the changes, they click the cancel button. Well, if your object's already been changed, that would mean you'd have to go back to the database and fetch the latest version to refresh memory. But if I were to clone the object first and only manipulate the clone, the original object is in place. So until I actually commit the changes of the clone to the database, I don't actually have to replace the original object in memory. So that's typically where I would do something like this. Another technique would be if I needed undo states in my program. So if, like, let's say you're working in like Microsoft Word, for instance, and you make some changes, or even in here. Let's say I'm in this browser and I make some changes, and then I start doing the undo. It brings me back to the original state of this cell. So the undo is basically keeping track of all the changes I made. And one of the ways to keep track of all of your changes is to clone the state as it was before the latest change. And obviously you can't do that indefinitely, which is why most editors of things like Illustrator, Word, they do have an undo limit of maybe 10 to 20 commands typically. Depending on the program, it might allow even more, but as you can guess, if you're always copying state like this, and you have a lot of state, that'll eat up a lot of memory fast. So those are the typical reasons I would use the prototype design pattern. There are probably dozens of other use cases, but those are the two that pop up into my mind as the ones I most frequently use it for.